Imagine you are teaching a computer to recognize whether a picture contains a cat or a dog. You have a dataset with labeled images. Some of them contains a cat and some of them contains a dog. The computer job is to learn from this data and be able to identify on new unseen images whether this image contains a cat or a dog. This task is called classification. Now let's explore the classification through well-known dataset MNIST. MNIST. I like this name. MNIST is a dataset that contains handwritten digits from 0 to 9. And the goal is to classify this image as a digit. We can visualize them with Python and then train a simple classifier. On the screen, you can see a Jupyter notebook running inside the VS Code. Yeah, it's just VS Code with hidden panels. No matter the challenge, everything starts with the data. So let's download MNIST dataset and take a look to the data. So we need to import sklearn datasets. Import fetch OpenML. Good. Then let's create MNIST variable and call fetch OpenML. Load MNIST 784 pixels and version 1. Okay, good. Let's check keys of our data set. Okay, here we go. It's just, bunch of keys like data, target, and fetch name, but the most important information condensed in data and target. Basically, it's our pictures with handwritten digits inside the data key, and target, it's bunch of labels. Let's separate pixels information and labels. Let's use X variable and variable Y. We use data for the X, target for the Y. We can check X. You can see it's a huge data frame, yeah, 70k rows and 794 columns. So most of the pixels that we see just completely empty, yeah, like 0, 0, 0. And here we have some information, yeah. And 0, it means that we have no any information, yeah. It's just completely like deep black pixel. And right here we have some intensity, yeah. Let's say that 0 means that pixel is not activated. So when we have a number that higher than 0, it means that this pixel is active, yeah, and we have some useful information that we can read. So a higher value means that we have higher intensity for this pixel. If we imagine the handwritten digit, most of the information on the image is just an empty space, yeah, definitely. So we can use ilog, and I believe if we use if we choose just the center of our row, we can catch more information. So let's choose from 400 to 500 pixels, and there is no surprise, yeah, we have much more activated pixels in the center of the picture, yeah. Okay, and let's right now take the first item from our data frame. Let's use ilog. We'll take the first item, and let's take the first item from our labels. So in this case, the label is 5, so the image represents 5. Finally, to see some images, we can use matplotlib. So let's import matplotlib, and then we need to create figure and axis plt.subplots. We can use 2 rows, 5 columns, so 2 times 5, just 10 images. And let's install the fig size, 10 times 5. And then we can iterate through our axis. We need to call axis.flat. We can use axis image show, and we need to take our x ilog. Let's use only first item. We need to reshape to 28 times 28. So yeah, we need to use values.reshape. You can see that it works. We can use color map, cmap equals to gray. Okay, now it's better. We can use axis off, and we can add some title, set title, and for the title we use y with the same index. We can also use plt.titleAuto and plt show. Let's use enumerate, and we have an index, so let's use this index right over here and right over there. Okay, let's run. Now we have some information from the dataset, yeah? And you can see that there is no surprise when we use center of the picture, yeah? It's much more information in the center, yeah, than from the beginning or from the end of our sequence. Once you have the dataset loaded, we can use a simple classifier like logistic regression to classify the digits. Logistic regression is a simple yet powerful classification algorithm. Despite its name, it's not a regression, it's a classification algorithm. It uses the sigmoid function to map predicted values to a probability scale. The sigmoid function can take any value and map it to the range between 0 and 1. Then we can set up a threshold and decide if our value less than, let's say, threshold equals 0.5, means that we have 0 class. If our value higher than the threshold, it means that we have class 1. Let me show you how a sigmoid function works. Now let's define sigmoid function with input x. Okay, and we need to import numpy. Let's generate a range of values x for our sigmoid function. So now let's transform this linspace with our sigmoid function. Okay, here we have a range, yeah, of numbers, very long range, yeah, 100 values, and then we just transform it with our sigmoid function, yeah, and you can see that we just change the range of these numbers, yeah, from -10 to 10. Right here we have values from 0 to 1, and I want to plot this sigmoid values. Okay, it's quite simple. plt.figure with the fig size 8 times 6. Okay, then we can add plt.plot. We need to visualize x against the x sigmoid. Let's rename it to y. Yeah, why not? X, comma, y. Okay, it works, yeah, but looks like I have a problem somewhere, yeah, because we have like flipped version of the sigmoid, yeah, just mirrored through the y-axis. Yeah, it means that we have some problems with our sigmoid. And yeah, I think that we need to calculate the exponent from the negative value of x, and in this case we just flip through our y-axis. Okay, I want to make this plot a little bit better. Now it looks much more better. Let's add a horizontal line that visualizes our threshold. For large negative values, you can see that the probability output of our sigmoid function just very small. Yeah, it approaches to 0. It means that it's a very low probability to be kind of positive class. Yeah, so it looks like we have a negative class. Yeah, or let's say 0. From the opposite direction, for very high positive numbers, we have very high probability to be a positive class, yeah? As the step number 1, logistic regression computes a linear combination of the input features. For example, with features x1, x2, etc., the linear equation looks like this. In this equation, W1, W2, etc. are models weights, and B is the bias term. And as the final step, we apply the sigmoid function to this linear combination. Y hat represents the predicted probability. Sigma z is the sigmoid function applied to this linear combination z, and transform it into a value between 0 and 1. And our prediction based on the probability. Regression assigns a class label 0 or 1 or whatever to each data point by applying a threshold. Usually we use 0.5. I can show you how the logistic regression transforms input to the output. Let's define the parameters for the simulation. Okay, we can define num samples and num features. Let's say that we have 100 samples and 3 features. Then let's create a variable weights. And we can use numpy random rand n, yeah, so we use num features, yeah, so we have the same number of weights as the number of features. For the next step, let's define bias. It equals numpy dot random dot rand n. We can use just one random number, it's totally okay. So then let's define x equals, let's say numpy random rand n, and we have number of samples and number of features. As the first step, this linear combination of features and weights are very easy to compute. So let's define variable z equals x dot product with weights and plus bias. Let's check the shape of the z. Okay, and you can see the result is just 100 vector with the length 100. Okay, and this at symbol, it's just the dot product, yeah, dot product between the matrix X and vector weights. As far as I remember, we have like 100 times 3 dimensions for the X, and we multiply this matrix to the vector weights, and of course in this case we have just the one dimension as the result, yeah, it's a number samples, and we just add a bias to the result of this computation. If it's not clear why we have a vector with 100 items, you might need a review of the matrix multiplication and the broadcasting rules. And for the next step, I just want to follow same notation. Let's create a variable y hat equals sigmoid applied to z. And I want to plot this y hat we have our sigmoid function. It's the same blue line as before, and we have a bunch of predicted values from our model. Yeah, of course it's not like a real model. Yeah, we just emulate weights with the random values bias, and we have no any optimization step. Yeah, we simulate the same like data structures, apply the same operations, and we can visualize the result, yeah, of this operation. And it's right over here. Yeah, we have a scatter plot, and we visualize z against y hat. We have values between like -6 and positive like maybe 3, yeah, and it converges without any problems to this probability scale, yeah. And remember, it was just the brief review, yeah. I don't want to look deeply into the logic regression, how it will optimize weights and etc. Okay, let's stop here and use the logistic regression from the sklearn. But first of all, you need to remember that we use y variable right over here, yeah? And we define x and y at the beginning of our notebook. Let's copy and paste it here. Okay, great. And let's import logistic regression. Also, we can import train test split. And let's import from the sklearn dot metrics import the accuracy score. Let's check one more time our dataset and labels. Yeah, for the dataset everything is clear. We have an integers. Yeah, but for the labels we have a string. Yeah, and I believe that we need to convert the string data type to the integer. So let's use y as type int. Test and train split, it's a commonly used practice. Yeah, you must train your model on one data and evaluate on another slice of the data. You need to train your model to predict labels, yeah, and then it will work on new unseen data. Let's create xtrain, xtest, and ytrain, ytest. Then we need to call train test split. Put here our data x, then labels y. Let's say that we use for the test just 20% of our data, yeah, 0.2. Let's install the random state 42 just to make the result reproducible. So now we need to create our first model. Let's create a model, logistic regression. We can define max iteration, yeah. Let's install like 2k iterations, yeah. Our logistic regression just trying to feed the data, yeah, for this maximum iteration steps. Then we can call model.feed xtrain ytrain, and our logistic regression just trying to adjust the weights of the model, yeah, accordingly with this data input. And then we used y pred for our prediction. We need to call model.predict our x test. At the first step, we train our model, install weights, and then we will call model predict with new unseen data, x test. This stage it calls training. We train our model on our data set, And this second stage, it calls evaluation. Yeah. And we have these predicted values, and then we need to compute the score. We can call our accuracy score, and we need to put y test, and we have y predict. So we train on train set, and we evaluate our model on the test set. And let's print our score right over here. Okay, good. Let's run this code. A pretty good score for such simple model like logistic regression, yeah, 91%. Okay, and this error, it means that our model just failed to converge, yeah. So total number of iteration reached limit. It suggests that we can increase this max iteration to, let's say, like 5,000 or more, or just scale the data as shown in the preprocessing. Yeah, honestly, I believe that our data is like much complicated than logistic regression algorithm can solve. Now, instead of the fine-tuning and playing with the hyperparameters, let's just analyze the results. And we have this code. This code can plot our images, yeah? Let's check for our X test, yeah? And we have the Y test right over here. Let's run this code. Okay, and instead of this X test I, we can use ilog. Right now we have a slice of the data from the X test, and we can add to the title just information about a true label and predicted label. Let's use our ytest.ilog as the true label, and then let's add the predicted label, and we have y predicted. So y predicted index. Let's run this code, and now we have an image from our data set and true label and predicted label by our model, yeah, and everything works fine. But right over here we have 8, and we predicted that it's like 5, yeah. So, and right over here we have true label 4, and we predicted that it equals 7, yeah, by somehow. So let's, instead of the data from the test set, let's take a look only for the misclassified images. We can use numpy.where. Right over here we put our y-test as the condition not equals to the y predicted. We can call it misclassified indexes. Let's check how it looks. Okay, it's a tuple, and we have only one item inside, so it means that we can take only 0, or we can use notation like this. So, and it's just a list now, yeah, in this misclassified index variable. Okay, and then let's use variable index. We can take misclassified indexes, and just let's take one item at a time from the misclassified indexes, and then we just replace this I by the index variable. Let's check how it looks. based on this output, yeah, sometimes it's not easy even for me to decide what type of the number I see. Yeah, it's 9, yeah, 9, but we predicted that it equals 7. But sometimes I don't understand why we just misinterpreted, yeah, the number. This 2, it's like pretty clear that this is 2, yeah, but we predicted that this item equals 8. From the debug perspective, this information is useful, yeah, but I can't say for sure what like type of mistakes like make most of the harm for our model. And we have a better way to visualize our errors. It calls confusion matrix. A confusion matrix is used to evaluate a model's performance by comparing actual and predicted results. In binary classification with only 2 classes, let's say positive and negative, the confusion matrix is a 2x2 table that breaks down the model's prediction to 4 categories. You can see how it looks. Our model predicts values, and we know that we have true predictions or true positive. It means that our model predicted this value correct. We have false positive, means that we incorrectly predicts the positive class. And same logic for the predicted negative, yeah? The model correctly predict with, it calls true negative, and false negative when our model just fails to predict the negative class. Let's consider a numerical example. Yeah, here we have a medical test for detecting a disease. Let's say kind of PCR test. Yeah? And we know that out of 100 people, 60 actually have the disease and 40 do not. So the tests correctly identify 50 out of 60 people to have a disease. It calls the true positive because we predicted this values correctly. Yeah, it's kind of true and it's really positive. Yeah, and we miss 10 and it calls false negative because it must be positive, but we predicted that this is negative, yeah, and it calls false negative. So we correctly identify 35 people out of 40 without the disease, and it calls true negative. Yeah, and we for the rest we have 5 false positive. Yeah, these people actually have no any disease, but we predicted that this 5 healthy people as diseased. Yeah. Why is it useful? Yeah, it helps to kind of break down the types of errors that our model makes. And you can calculate important metrics like accuracy, precision, recall, and F1 score based on the values in this matrix. This simple 2x2 matrix is a clear way to analyze binary classification performance. But for the MNIST classifier, we have 10 possible scenarios, yeah? It means that we have 10 by 10 matrix, because every number can be misclassified with all of the rest, yeah? So let's build this matrix. Okay, and now let's build a confusion matrix for our predictions for the MNIST dataset. Yeah, and I have this function plot confusion matrix. Yeah, basically you can use the Seaborn for this purpose. Yeah, but I have a trouble with dependencies, and that is the reason why I just created this very simple function. So We have a confusion matrix function from the sklearn matrix, and this function plot confusion matrix. We receive our true labels and predicted labels. Let's rename it to y and ypreds. Okay, great. So as the first step, we generate the confusion matrix for our scenario. Then we build a plot and use image show to visualize the confusion matrix. So then we annotate each cell with the numeric value of the confusion matrix. We use kind of coordinates x and y. So yeah, now it's better. Yeah, we have the coordinate y as the first level of this loop and coordinate x as the second level. So then we just display the plot. Let's run this code, and here we go. It's our confusion matrix, yeah? Let's clarify the confusion matrix for the MNIST classifier. And diagonal element or true positive elements represents correct predictions of our model. For example, 1284 times we correctly identify 0 as 0. 1555 times 1 as 1, and so on and so forth. For the columns of the confusion matrix, as far as I remember, we have false positive items. It means, let's take, for example, class 0, yeah? It means that we identify this picture as 0, but actually it was 2, yeah? It's false positive. For this example, 4 times images were actually 3, and we predicted as 0. For this cell, 8 times our images were actually 4, and we predicted as 0. 13 times images represented 5, and we predicted as 0, and so on and so forth. For the row, as far as I remember, we have false negative scenarios. It means that once we our image was actually 0, and we misinterpreted this image as 1. 8 times our images were actually 0, and we predicted as 2. And let's say 11 times our images were 0, and we predicted as 5. Let's take, for example, this line, yeah? This class 5. Then 94 times we correctly predicted 5 as 5. And 18 times our images were actually 6, and we predicted as 5. 6 times our images were 7, and we predicted as 5. And for the row of this class, yeah, we have 23 images that were actually 5, and we misclassified these images as 6. Once we misclassified 5 as 7. 48 times we misclassified 5 as 8, and so on and so forth. So you need to follow always the same logic. On the main diagonal, we have true predictions. On the column for the class, we have false positive scenarios. On the row items, we have false negative scenarios. And the confusion matrix, it's very important. From the confusion matrix, we can calculate various performance metrics that can give us some insights about the model. Let's build an accuracy, for example. Let's create a variable accuracy, and it's going to be equal the trace of the matrix, of the confusion matrix, yeah, we just take the sum of the main diagonal elements. We need to call cm.trace for this purpose, and we need to divide it by the sum of the all elements in the matrix. So confusion matrix dot sum. And let's check how it looks. Yeah, and it works fine. Yeah, you can see that we have pretty the same result as we did from this example. We just have exactly the same match. Yeah, let's compare it by very bad way. Yeah, but let's do it like this. So you can see that this is exactly our accuracy that we computed before with the sklearn. The proportion of correct prediction over the total number of predictions or total number of instances is the accuracy score. Yeah? Correct predictions, it's right over here. Yeah, it's the numerator of this proportion. Yeah, it's just the sum of diagonal elements over the total number of instances or total number of predictions in our confusion matrix. And you can see it right over here. Yeah, on the main diagonal we have the correct predictions. Yeah, and everything else it's just the bunch of mistakes. Yeah. The next metric is the precision metric. And precision, it's a metric that tells us the accuracy of the model's predictions for each class. In other words, it answers the question of all the instances that model predicted at a particular class, how many were actually correct? And we know that we have true positive predictions. It's like predictions of our model that actually correct, and false positive when our model just misinterpreted by somehow our class with another class. So the precision formula, it's right over here. Yeah, we divide the true positive predictions over the sum of true positive predictions and false positive predictions. So we just wanted to know how accurate our model estimated this exact class. We can easily calculate predictions using sklearn. Let's import from sk.matrix, let's import the precision score. And let's compute precision per class. We need to call precision score. And we have approximately the same bunch of parameters, y-test and y-pred. And then we can build a loop. We will iterate through all of these results and just print the precision metric for every class. Let's run this code. And we have a trouble with the parameter average. Yeah, by default our precision score just work for the binary classification problem. Yeah, but in our case we have like a bunch of classes. Yeah, we have 10 classes, and in this case we need to put average none. Yeah, we can check the documentation. Yeah, and we can see that the average, if none, the scores for each class are returned. Okay, and let's run this code again. And here we go, yeah? And it's very interesting, yeah, that precision for class 0 equals like more than 95%, but for the class, let's say 5, we have just only 88%. And it's very useful information, because some of the classes make more harm than the others for our model's predictions. Okay, to reproduce the same results, let's first of all just create a new confusion matrix isolated in this cell. Then let's create a list and let's call it precision per class. Then we need to iterate through all of the classes and the confusion matrix. We can create a loop in range, and let's use the length of the confusion matrix. In this case, we just use one dimension of the confusion matrix. In our case, it should be equals 10. Let's check it. Yeah, it works fine. Yeah, it's just only 10. So for the next step, we need to take the diagonal element, yeah, because we know that the true positive, and we need to have the true positive, it's just exactly at the main diagonal. Let's create a variable true positive. It equals to confusion matrix, and to take the main diagonal element we need to use the same index twice. Yeah? I mean, let's check it one more time. Yeah, here we have an element 0 0, here is just 1 1, 2 2, 3 3, 4 4, and so on and so forth. So if we just duplicate the index, yeah, and use it right over here, we have true positive elements. Yeah, and it's just our numerator, yeah, true positive. And in the denominator, we have a sum of true positive and false positive. And for the false positive, we know that the false positive, it's a column from the confusion matrix. Yeah, and we can take from the confusion matrix column for the class I. Yeah, so we take all of the items from the column. Yeah, and if you want to have only like false positive, we need to sum items from this column and then just subtract the true positive values. So in the first line of this loop, we have true positive for class I, and for the second line, we have false positive for class I. Yeah. Okay, let's just check that we really take a column from this matrix. Yeah. Let's say that we want to take a column for the class 0. And here we go, yeah, it's exactly this column, yeah, 0, then 6, 4, 8, 13, 7, 4, 11, 6, yeah, we just take this column. So we can take column 1, yeah, no problem at all, yeah, it's just exactly the column 1, and so on and so forth. If we need quite opposite, let's say we need to take a row, we can use this pattern. Yeah, let's take for the class 9 just the row from the confusion matrix, and you can see that it works exactly as we expected. Yeah, we take this row, and let's think for a moment. Yeah, actually for the numerator we need to have a true positive values for class I. And for the denominator, we need to have a sum between true positive and false positive values. So we can drop this. And actually, we have false positive plus true positive values in this exact line. Yeah. And now let's compute the precision. True positive over the false positive and true positive sum. But you need to remember, we have a fraction, yeah? And in the numerator, somehow we can have 0. In this case, we need to check that if our sum more than 0, yeah, everything works fine. Yeah, we need to run this expression. But if it's not, we need to return just 0. So we use this expression, yeah, to avoid division by 0. Okay, and for the last step, let's add to precision per class. We use append this value precision. Okay, and let's print this metric precision per class. And here we go. And you can see that this is exactly the same result. Yeah, we have the same result as we did before with sklearn, yeah, precision score function. For summary, precision measures how accurate the model's positive predictions are for a specific digit. Yeah? We have in the numerator true positive predictions, and in the denominator we have a sum of true positive and false positive predictions. And as far as I remember, we have two types of errors: false positive and false negative. False positive in column of the class, false negative in the row for a class. Precision metric is very important if you care more about being accurate when you do predict a certain digit, yeah? In other words, minimizing mistakes when our image, let's say 3. And in this example, you can see how it works. If the model predicts 100 images as 3 and 90 are actually 3, the precision for class 3 is 90% or 0.9. And the recall metric, from the other hand, just measure how well the model finds all instances of a specific class. And in this example, you can see if the model correctly identifies 90 out of 120, the recall for class 3 is 75% or 0.75. So we have two different questions and two different answers from this matrix, yeah? Precision for class 3. It means that all of predicted 3s, how many were actually 3? And recall for 3, of all actual 3, how many did the model correctly identify, correctly catch, yeah? In sklearn, we have recall score, and we can compute the recall for each class. Let's then print recall for class, and you can see the result, yeah? And again, the recall metric is different for different classes because we compute recall for each class separately. Okay, and we can easily reuse this class, this code for the precision. And let's change it to compute the precision instead of the precision, just recall matrix. Okay, it's not the precision, it's recall. Okay, good. Then, as far as I remember, right over here, we have sum of the false positive and true positive. But instead of this, we need to have false negative and true positive sum. And to compute the sum of false negative and true positive, we need to take, as far as I remember, again, yeah, when we use this construction, let's check, yeah, how it works. And let's take, for example, class 9. When we use this way, we just slice a column of the confusion matrix, yeah? But we need to swap this, and in this case, we just take a row from the confusion matrix, yeah? Let's say we can take the last row from the confusion matrix, yeah? And yeah, here we go, it works fine. Okay, and we need to swap the column and index, right, over here. So right now we take just false negative and true positive. Let's try to calculate the recall, and there is no surprise. because we use the same way to compute the recall metrics from our model. The F1 score is designed to provide a balanced measure of a model accuracy by combining precision and recall. The F1 score, or the harmonic mean of precision and recall, especially useful when we need to account for both precision, and we know that precision is the accuracy of positive predictions, and recall, it's just the measure of capturing all true positive. We use the harmonic mean because it's better for some edge cases and better for low or high values. Let's say that we have precision 1 and recall 0. In this case, we have 100% of precision and 0 for the recall. Arithmetic mean, it will be just 0.5 because we need to sum up 1 plus 0 over 2 items, and we have 0.5. But for the harmonic mean, we have just 0, yeah, because we need to in the denominator we multiply 1 times 0 over 1 plus 1 plus 0, yeah, and multiply it by 2. And of course in the numerator we have just 0, and the result equals 0. For our previous examples, when we predicted 100 images as 3 and 90 actually 3, the precision equals 0.9. And we have recall, yeah, when our model correctly identifying 19 out of 120, we have 0.75 recall. And in this case, the F1 score, it's approximately equals to 0.81%. This formula combines precision and recall, and in this way we can be sure that both metric must be high to achieve the high F1 score. It's very useful metric. So let's program the F1 score. And here we go, yeah, it's approximately the same API, yeah, and we have not so bad F1 score for most of the classes, yeah, but we have a little bit lower value for the class 8, yeah, just 86%. And for the class 5, we have 85%, yeah, and again, by the same logic, some of the classes just make more harm than the others. Okay, and we have the same result, yeah, it's right over here, yeah, it's completely match, yeah, between this one method from the sklearn and between the method that we programmed by our own. But we missed one important thing, yeah, we need to check that if this one is more than 0, we return the computation of the F1. In any other case, we need to return 0 to prevent the division by 0. Okay, and it works fine, yeah, it works fine. Now I want to visualize these three metrics, precision, recall, and F1 class side by side in one table. First, we need to compute precision, recall, and F1 per every class. Then let's import pandas. We can create a simple data frame to store these metrics per class in this table. Let's run this code. You can see that sometimes for, let's say, for the class 8, we have a smaller value of the precision metric and smaller value of the recall. And these both metrics produce the lower F1 score. As far as I remember, it's a harmonic mean. And for this one, yeah, for the class 5, we have smaller version of the precision and smaller version of the recall. Yeah? MNIST dataset has mostly good balance for the items of the dataset. but some classes may have more examples than others, and it means that we can have small imbalance between the classes, and we can see it right over here. Yeah, we have different performance for the classes. Maybe some of the image classes just not so good from the quality perspective, yeah, but maybe some classes just underrepresented in the dataset. So we have one parameter, very useful parameter in the logistic regression model. I copy and paste the model code right over here, yeah, just absolutely the same code as before. Let's change the max iterations to 1k instead of 2k, and let's add one more argument, plus weights, and I want to use balanced. It can help to focus model more evenly between different classes. So I want to copy the cell output. Let's just preserve this result right over here as the previous result. Okay, and let's run our code again. This shows us slight difference from before. Yeah, you can see that our model in some scores we have a bump, yeah, but not so big difference between, let's say, this item and this, yeah. Right over here we have 0.9572, and in the previous result we have 0.9560, yeah. But for some lowest values like this 5, yeah, we have a little bit more bump, yeah, but it's still like, it's very insignificant changes, yeah. So, but it's important, yeah. We right now just evenly align and treat all the classes, yeah. For our model, it can be very, very important if we will continue to, let's say, preprocess our data or make some feature engineering. It's good to have. I want to improve my model performance, and we can see this error message that we failed to converge because our model just reached the iterations limit. And I suppose that if we will increase the number of iterations, it won't help us a lot, but we can try to play with the data. As far as I remember, we use the logistic regression, and logistic regression work with the sigmoid function. And when we have data in range between 0 and 255, for the first steps, our model just changed the range of our data and adjusted the weights to make the data in appropriate range, yeah. Because if our data in range between 0 and 255, we're very skewed to the top side of the sigmoid. And I think that if we rescale our data, it can make an impact to the performance. Let's import from sklearn Preprocessing, import the StandardScaler, and we need to create a scalar like a standard scalar. Okay, and then we need to create x train scaled as and we need to call scalar dot fit transform and put right over here x train, and we need to do the same for the x test. We will create x test scaled equals to scalar dot fit transform. We need to put right over here x test. Now let's check the data. We need to call xtrain values, and I want to take the first item, and let's say the cells from 400 to 500 in the center of our image, yeah, because we have an image as a bunch of pixels. We have much more information, and we need to check X-train scale as the next step. Let's check the same range for the X-train scaled. And of course, we need first of all to run this scaler. Scaler just rescale our data. So now you can see that our data from the range between 0 and 255 just rescaled to the range between, let's say, negative 1 point something to maybe positive 1 point something. Yeah, I can see the exact example. Yeah, right over here. Yeah, positive 1 point something. Yeah. And to understand how it works, let's check the formula. Our StandardScaler is a preprocessing tool that transforms our data. So each feature has a mean 0 and a standard deviation of 1. This process is called standardization. You can see that as the first step, we're subtracting from each feature the mean, and it's just centering our data around 0. And as the second step, we divide this result to the standard deviation, which scales the range of values to have a standard deviation of 1. This transformation makes the data normally distributed around 0 with consistent spread. It can improve our performance because right now we have a consistent range of data spread around the 0. Finally, let's visualize how the scaling actually affects our images. Yeah? And I have this code. We can choose any number. We just need to save it to this variable. Then we just filter our labels accordingly with the chosen digit and save it to digit indices, and select from X-train and X-train scaled our images. I suppose that it would be enough to represent, let's say, just only 5 images from the dataset. So then I have this plot with just 2 subplots, and at original image from one side and from the other side I have scaled image. Okay, it looks like this. Here we have the original image, here we have the scaled image. It works like good, but I see that sometimes some areas is brighter than the others. I have a kind of strange like shadows. Maybe it can make the performance of our model better, or maybe it can make it worse. Yeah, so we need to check how it performs now. We can copy this code. Yeah, so let's copy and paste it here. Then we need to take X-train scaled instead of the X-train, and X-test scaled for the evaluation. Good. Let's run this code. Okay, and now it performs a little bit better. Yeah, I just can compare side by side. Yeah, let's say this performance of the class 5 and compare it with this one. Here we have 0.8770. Here we have 0.8767. Yeah. Right here we have 0.8982. Here we have 0.8989. So it's just bumped the performance just a bit, but it's like nothing special. Yeah. Let's check how this StandardScaler works for different numbers. Let's take, for example, 0. Okay, and you can see that some areas just slightly brighter than the others for the 0. Or let's take, for example, class 5. Okay, we can see that it's yeah, quite strange. Yeah, we just have this bright areas, and I don't like this bright areas. Yeah, I believe that it can make a small confusion for our models. Yeah, but this slight bright areas, it's not everything. Yeah, for some pieces of the image you can see this shadow, yeah, that from one side just a little bit brighter than from the others, but it's not the only problem. Yeah, sometimes we have this like areas that a little bit darker than the others. Yeah, and we have some sort of circle around the number. Let's check, for example, 8. Yeah, and for 8, it's quite obvious that we have this bright areas. Yeah, we have this like dark shadows, and I think that it can make a confusion for our model. So let's try to use different scalars. And for example, we can use MinMaxScaler. In other words, the StandardScaler just broke the relationships between our data by somehow. Yeah, and you can see it right over here after our visualization. We have one more useful option. It calls the MinMaxScaler. So let's try this one. We need to create scalar as the MinMaxScaler. And it works like this. We subtract from the x the minimum value from our data set and divide it by the max minus min. And it's just rescale everything to the range between 0 and 1. So let's run this MinMaxScaler. Then let's check our data again. And you can see that we preserve the data relationships. Yeah, you can see that we have the same 0 0 from the beginning of our sequence. Then we have this scaled 4 scaled cells, then again 0 0, and so on and so forth. We completely reproduce the same data structure, and it will work for the images much more better than the StandardScaler. Let's run this visualization, and you can see that it works much more better. Yeah, because right now we have no any shadows, any brights. Yeah, we preserve the same type of relationships between our data using the MinMaxScaler. Let's try to run our logistic regression, but before, let's save this result, and now let's run this code. Obviously we have the higher score. Yeah, most of the classes perform better than the previous result with the StandardScaler. Right over here we have 0.902, here we have 0.898, and so on and so forth. So in average we have better performance compared to the rough pixels and compared to the pixels that scaled with the StandardScaler. Most of the information on the picture of handwritten digit, just an empty space. Maybe we have a way to reduce the dimensionality of our picture. And yeah, we have something that we can do with this. Principal component analysis is a technique to reduce the dimensionality of data when we need to preserve as much information as we can. It is very useful when we have high dimensional data. Principal component analysis always used to reduce the amount of features, but we save most of the information about patterns in the data. And PC identify the kind of directions in the data where we have the highest variance. On the screen you can see the principal components of a Gaussian distribution. The vectors that you can see on the screen are eigenvectors of the covariance matrix, scaled by the square root of each eigenvalue and positioned at the mean. To apply the principal component analysis to our data set, we need to import from the sklearn decomposition PCA. Okay, and I see small trouble right over here. First of all, we need to feed the transform, yeah, for our X train, and then apply this transformation to the X test. Let's rerun it just to make it clear. I don't think that it will be a big trouble, yeah, but to be more precise, yeah, we need to fix this. Let's create a PCA variable. We need to call PCA, and we need to set up the number components. Let's take from the beginning, for example, just maybe 10 components, yeah? And then we will see how it performs. So we will apply our PCA to the X train scaled. And let's create a variable X train scaled PCA. And we need to call PCA.feed transform and provide here our X train scaled. And then when we feed the transformation, we need to apply the same transformation for our X test scaled. Let's create one more variable, X test scale PCA. It equals PCA transform. And we need to provide X train scale to this transform. Okay, great. Let's run this code. Okay, it looks good. So now we can check by the same way how our data looks. Yeah, let's call the X train scale PCA, and we need to take, for example, our image number 0. And here we go. Yeah, it's just 10 components. Yeah, we represented the whole image as 10 principal components. How can we decide that we have enough data? Yeah? I think that we can apply the inverse transformation and plot our image side by side near with the scaled image. Yeah, because principal component analysis is just pure, in some sense, yeah, pure mathematical operation. It means that we can apply the inverse transform. So let's create a variable X train scaled PCA restored, and we need to call PCA dot inverse transform and put right over here X train scaled PCA. As the step number 2, let's just create one more variable, X train scaled PCA restored selected. Yeah, just selected slice of the data that we need. And we put right over here just our indices that we need to take from our restored variable. Okay, great. And here we need to create a PCA restored image. We need to call X train scaled PCA restored selected, provide an index I, and reshape it accordingly as our image. So we need to add to our subplot one more image and plot the PCA restored image. Okay, good. So we set up index number 2. Here we have PCA restored image, and we need to put this image right over here. Okay, good. Let's run this code. And here we go. It looks slightly similar with one, yeah, but I don't think that we preserve enough information to restore an image yeah, in high detailed resolution. Yeah, it looks slightly like 5, yeah, but sometimes just complete mess. Yeah, I cannot identify what does it mean. Yeah, what is it? Yeah, it's not enough components. So let's increase this number to, let's say, 30 components, and then run this code. We can check, yeah, the shape of the transformed images. Yeah, and right now we have 30 components, yeah, for representation of our handwritten digit. Let's run this code to plot the images, and you can see that it's much more better. Yeah, we can clearly identify most of the time our 5 image on the restored picture. Okay, but what if we just set up, let's say, 60? And you can see that right now we have 60 principal components, and let's run this code. Great, and it looks like clearly like 5. Yeah, most of the time we can see that it looks like 5. Let's take, for example, 8, because I believe that most of the mess will be on 8. But even for 8, it looks much more better. Yeah. So I hope that right now we can take this scaled PCA version of the data and run our logistic regression and try to fit this PCA version of the images. We need to replace this X-train scaled to PCA, X-train scaled PCA, and replace X-test scaled to X-test scaled PCA. Okay, I have this results. Yeah, let's run this code. Okay, it works much faster. Yeah, and we lose just only several points. Yeah, so we have a performance 0.9129. And for the full version of the picture, with MinMaxScaler applied to our data, we have 0.921. Yeah, it's approximately the same performance. Yeah, slightly lower. Yeah, closer to our StandardScaler result or to our original result, but we lost not so many information. Let's add a little bit more components. Let's say 80. Let's run this code. Then we can see that instead of 60, we have 80 components per every image. Then let's try to visualize our images. And yeah, now it's pretty clear that it's like 8. Yeah, no problem to identify 8 on the picture. Or let's say 1. Yeah, for the 1, it's absolutely clear that most of the pictures looks good. Okay, let's run our logistic regression again. Okay, and here we go. Yeah, we have a slightly higher result than our previous run. Yeah, but still lower than after MinMaxScaler. So let's use 100 components, and then let's visualize our data. Yeah, I don't see a big difference, yeah, but maybe for this number it's a little bit more clear. And let's run this code again. Our previous result, it's like score 0.91664. Okay, let's see how it looks for the next run. Obviously, we can't reproduce the same score as we did with original image information and MinMaxScaler applied to this image. Yeah? We have much less information, yeah, when we apply the PCA for our pictures. And you can see that restored image looks slightly blurry. We have like this. Yeah, we have some noises and it doesn't look quite like accurate. Yeah, of course we can increase the number of the principal components and it will be much better. Yeah, but we have very big advantage. We have 100 components with principal components analysis. Yeah, these 100 components capture most of the important information, most of the important patterns on our picture, and it's a much smaller slice of the data. Yeah, it's a much smaller set, and we can make some transformations even further, yeah, but little bit faster and more efficient if we will apply, let's say, for 784 features any transformation. It can be painful, yeah, but for 100 it's not so bad. And I know about one very effective technique that we can apply to this reduced number of features. It calls the polynomial features. And I can show you a quite simple example. Suppose that our PCA just reduce our image dimensionality only to two components, like x1 and x2, yeah? It's impossible, I think, to use just only two components, but let's just, for simplicity, make only two. And polynomial features with degree 2 would expand this to x1 and x2 as the original component. Then it will apply square every terms and make an interaction terms between our features. Okay, and let's consider an example with three features, x1, x2, and x3. We, with degree 2, we include like each feature itself, square term of each feature, and interaction term between pairs of features. And you can see how it works. Yeah, original features, square term for each feature, and interaction between every pair of features. And for our example, when we apply polynomial features with degree 2, this step creates new interaction terms between 100 principal components, allowing the model to capture much more relationship between this data. And I think that this bumps our score much more further than increasing of the number of principal components. So let's import our polynomial features. Let's create a poly variable, and then we need to call polynomial features. Degree, let's choose second degree. It's totally okay. And we don't need any, let's say, bias. Let's install the include bias to false. We don't need bias to, term. And now let's create X train poly. And we need to call poly.feed transform. Then we need to provide our data. So as the data, we will use the X-train scaled PCA, yeah, whatever. And then we need to create X-test poly. And we need to call poly.transform. And put right over here our X-test scaled PCA. Yeah? We can apply the polynomial features just only for the reduced dimensionality. For 784 features, it would be like disaster. Yeah, too many dimensions. Okay, and now we need to visualize our data. So let's choose from the X-train poly. Let's choose our indices. It's impossible to plot the picture, yeah, but we can plot the histogram for the polynomial. Okay, let's run this code. Yeah, we need to add one more subplot. We have not 3, we have 4 subplots. Okay, great. And now you can see how it looks, yeah. Our data definitely has some skew to the left side, yeah, and we can see that some features dominates compared to the other. Let's now just apply our logistic regression for this kind of transformed data, X-train poly. I hope that we catch some additional dependencies, some additional bindings between the data when we apply this feed transformation. Of course, feed transformation of the polynomial features. So great, let's copy this data. And we need to run the logistic regression, but not for the X-train scaled PCA, yeah, but for the X-train poly and for the X-test poly. Okay, Now let's run this code. Okay, here we go. You can see that the score, it's 98%. It's much more higher than everything that we did before, yeah? It's much higher than MinMaxScaler. It's much higher than the original predictions, yeah? It's quite perfect. To be honest, I didn't expect that it would be something like this. Yeah, it's very high. Probably if we will try to fine-tune our model even further, we can reach even higher score, yeah? But I think that it's totally enough, yeah? And the result shows us the effectiveness of combining dimensionality reduction technique with polynomial expansion on scaled data for the maximum performance.